Here's the solution to my challenge problem that we worked on in class today about absolute values. And what we're told to do in this problem is to solve this equation right here, to solve it graphically and algebraically, and then to compare our results. And anytime you have an equation with a single variable and you want to solve it graphically, what you do is you find the values of x where these two graphs intersect. In particular, I'm looking to graph these two equations. So what I did was I took the left-hand side of my original equation with a single variable and I set it equal to y. And I took my right-hand side of my original equation and I also set it equal to y. And I'm going to graph these two equations and figure out where they cross each other. And so starting with the absolute value equation, there's a few things that you should know by now after being in this class for a couple weeks, is that the vertex of this thing is going to be at x equal to -4 and y equal to -1. That's this point right here. And then I'm going to use this multiplier, 5/2. We treat it kind of like a slope in this case. And what I can do from this point is I can just go up 5, 3, 4, 5, over 2. Up 5 over 2, right? And I'm able to construct the right-hand half of my absolute value. And just to get the other half, up 1, 2, 3, 4, 5 over 1, 2. And I could keep doing that, but I get a couple of points, and then I can draw the second half. So this V-shaped graph is the graph of this absolute value equation. And then simply enough, I can graph this line by just going to the y-intercept, -2, and going a slope of -3, I go up 1, 2, 3, and over to the negative side, 1, 1, 2, 3, 1, and so on. And then there's my y equals -3x minus 2. Well, these two expressions here, when they're equal, that's when the x value and the y value are the same. And so that's really at the point of intersection. And on my graph, I just show one point of intersection here. And x equals 2. And that's my solution. And to kind of help us think about whether or not there are any other solutions. And sometimes absolute value equations, of course, they have two solutions. But let's think about this. The slope of this line is -5/2, right? Which is like -2.5. And the slope of this line is -3. So let me do kind of an exaggerated idea here. This line, imagine it's got a steeper slope than this one. So these two lines are actually diverging. This line and this section of the absolute value line are actually moving farther and farther away from each other. So I made a little note here. They're never going to intersect. So I know there's only one solution according to my graph. So let's see what happens algebraically over here. So I just begin by copying my equation down here. And then I just follow use my properties of equality first to multiply everything by 2. And then I'm going to add the 2 to the other side, and then I divide both sides by 5. That's what happened here. And now my absolute value is isolated on the left-hand side of this equation. So I can split this into two separate equations. Here, I just take the x plus 4 equals this right-hand side, or x plus 4 equals the negative of the right-hand side. And notice I just multiplied this thing by -1. That just resulted in all of these negative terms on the top of my fraction becoming positive. And so this is our strategy for solving absolute value equations. And if I work this equation on the left, multiply everything by 5, moving the terms around, using the properties of equality, and ultimately getting to a value of x equals -2. Oh, I see a little error. There we go. That agrees with my solution over here, x equals -2, adding that negative sign in. Okay, and so I've confirmed this solution graphically. But what happens over here? When I solve this equation, multiply both sides by 5, and the same properties of equality lead me to x equal to 18. And I submit that this is an extraneous solution. First of all, think about the graph. When x is 18, I'm like somewhere way out here. And you can see that there's no possible chance of this part of my absolute value graph and this part of my line intersecting way out here at x equal to 18. So this solution seems extraneous. And I can demonstrate that by, once again, going back to my original solution here, my original equation, and then I substitute that 18 in here. And when I work out the math, I get this sort of mismatched equation. 54 is not equal to negative 56. So that again leads me to conclude that x equal to 18 is an extraneous solution that's introduced into this equation when I employ this algorithm, particularly right here when I split this into two halves. So that's what we're really looking for when we're talking about comparing our results for the graphical and algebraic solution. Our graphical solution shows us just one possible point of intersection. We even thought a little bit more about what happens when x gets really negative and when x gets really positive. There's only one point where these two graphs will intersect, and it's when x is equal to negative 2.